Behind every single app you use, every website you scroll through, there's a set of instructions, an algorithm, that's basically telling the computer what to do. But here's the kicker. Not all instructions are created equal, not even close, especially when you go from dealing with, say, a handful of things to millions. So let's pull back the curtain on this hidden world of algorithm efficiency.
Okay, just picture this. You're sorting photos on your phone. If you've only got like 10 pictures, it's a piece of cake. It's instant, right? But what if you had 1,000,000 photos? Suddenly, how you sort them becomes a massive deal. I mean, a really smart way to do it might take a second, but a clumsy, basic way, that could take minutes or, maybe even hours. That right there is the problem of scale. And it's exactly where this whole idea of efficiency becomes absolutely critical.
Right, so that leads us to the big question. When you've got a bunch of different ways to solve the same problem, how in the world do you find the fastest algorithm for the job? How do we pick the winner?
So, what's the first thing that pops into your head? Probably the most obvious solution, right? Let's just time them. I mean, why not just run both algorithms on a computer and see which one finishes first? It sounds perfectly logical. Let's get out the stopwatch. And yeah, this is pretty much exactly how you'd set it up. You'd create a massive chunk of data, you'd start a timer, run the code, stop the timer, and then you just write down the time. You could do it over and over with bigger and bigger sets of data just to see how things change. Super simple, direct, it's a classic experiment. But wait a second, is this really a fair race? I mean, think about it. If I run my test on a brand new, souped-up gaming rig, and you run the exact same test on a 10-year-old laptop, are we actually measuring the algorithm, or are we just measuring how good our computers are? Yeah, this simple question kind of blows a huge hole in our plan. Well, it turns out the results you get are completely at the mercy of the environment. We're talking about the machine's CPU speed, how much RAM it has. Heck, even how many other programs you have running in the background can totally skew the results. So, the bottom line is this. Just timing things with a stopwatch is not a reliable, universal way to judge how good an algorithm actually is. So what we really need is a universal yardstick, a way to talk about an algorithm's performance that is totally independent of the hardware and the environment, something that measures the core, underlying logic of the algorithm itself, no matter what computer it's running on. And this is where we get a universal measurement. We're going to shift our thinking, moving from counting seconds to looking at growth rates. It's a total game changer. This brings us to a really key idea called time complexity. Basically, we stop thinking about seconds altogether. Instead, we just count the number of basic steps, the basic operations an algorithm has to do. And we describe that count in terms of n, where n is just the size of whatever we're working with. Now, the fancy term for this whole approach is asymptotic analysis. And that word asymptotic is super important. All it really means is that we're most interested in how an algorithm behaves when the problem size n gets really, really big. Because let's be honest, that's when performance differences truly matter. All right, so to actually talk about all this, to decode this language of efficiency, we need a special kind of shorthand, and that shorthand is called Big O notation. So what is Big O notation? Well, think of it as a way to describe the upper bound, basically the absolute worst case scenario for an algorithm. It tells us, as our problem gets bigger and bigger, just how fast the number of steps is going to grow. It's pretty much the standard way we talk about an algorithm's efficiency or its cost. Okay, check this out. Here we have a table of the typical growth rates, and it's like a leaderboard for efficiency. Up at the top, you've got the rock stars, constant and logarithmic. They're incredibly fast. But as you move down the list to things like quadratic or, heaven forbid, exponential, things start to get really slow, really fast. Those are the ones you try to avoid if you can. And if you want to see just how insane that difference can be, look at this. Let's say our input size is 10,000. A nice, simple, linear algorithm that's O of n is going to take about 10,000 steps. Makes sense? But a quadratic one, O of n squared, it doesn't take 20,000 steps, it takes 100 million steps. The cost just completely explodes. It's not even in the same ballpark. So this really boils down to one simple golden rule. The slower the asymptotic growth rate, the better the algorithm. Period. You want the one that can handle more and more data without breaking a sweat. Okay, so here's the quick and dirty way to figure out the Big O.
When you're looking at the math that describes the number of steps, you just do two things. First, you drop all the constants. They don't matter in the long run. Then you get rid of all the smaller, lower-order terms. All that matters is the single biggest, fastest-growing term. In this example, the n squared term is the heavyweight champion, so the whole thing is just O of n squared.
All right, enough with the theory for a second. Let's put this into practice with a classic case study, the search party. We're going to compare two ways of finding something in a list, linear search versus binary search.
So first up is linear search. This is the brute force method. You just start at the very beginning and check every single item one by one until you find what you're looking for. The worst case scenario, you have to check everything. That's why its big O is O of n. Now, binary search is way smarter. The catch is your list has to be sorted first. It starts by looking at the item right in the middle. If what it's looking for is bigger, it throws away the entire first half of the list. If it's smaller, it throws away the second half. It just keeps cutting the problem in half over and over again, and this divide and conquer strategy gives it an absolutely incredible big O of log n.
And here is where your jaw hits the floor. To find just one item in a list of 1 million things, a linear search could, in the worst case, take 1 million steps. But a binary search? By cutting the list in half each time, it will find what it's looking for in, wait for it, at most about 20 steps. 20! That's not just a little bit better, it's a totally different reality of performance.
So let's bring this all home. Why does any of this efficiency stuff actually matter? Well, it's because this isn't just some abstract theory. This thinking is what powers your daily life. Think about it. Every time you type something into a search engine and get results back from billions of pages instantly, or you scroll your social media feed and it just knows what to show you, or your GPS finds the fastest route avoiding traffic, you are personally benefiting from incredibly efficient algorithms. These things simply would not be possible without them.
And that's really the heart of it. This focus on efficiency, this whole big O thing, it's the invisible architecture that makes our entire digital world feel so seamless and instant. It is literally the difference between technology that feels like magic and technology that would be painfully, unusably slow. So the next time you use an app and it feels incredibly snappy, or a search result just pops up like magic, maybe just take a second to think about the insane amount of efficiency that's humming away behind the scenes. And it leaves you with a question to ponder. What's the hidden efficiency cost of all the apps and systems that you rely on every single day?